Okay, so I apologize for being gone today. That's okay though, we're still gonna move on in notes and you will still have homework tonight. So we are going to do the notes for Unit 11, Section 2, and your homework will be page 321, 1 through 5. So please make sure that you pull out a piece of paper right now and put that your homework is page 321, 1 through 5. And you do need to do that right now because unlike previous days, I'm actually going to require that you write down your answer to the clicker questions as we go along as well. So remember those questions we have throughout the presentation? You have to write down your answer for each of those as we go along. That will be part of your homework credit. So if you have not already, please make sure you've pulled out a piece of paper, have it in front of you, ready to go. Make sure you put that your homework is page 321, 1 through 5, and that will be due tomorrow, which is Thursday, March 25th. Okay, hopefully you have that ready. Make sure you have your notes in front of you. You need to open them to section 2. So I think it's 2 pages you have to turn, and we shall get going. Luckily, these notes are just a continuation of yesterday, so I do not believe that they should be that horrible. Make sure that you are writing down your answers to the clicker questions as we go, and I will remind you. So as you can see, we are continuing with our Unit 11, Evolution of Populations. Here's this population of the emperor penguins that we saw yesterday on our notes. By this point, hopefully you are thinking of differences in that population. The fact that maybe one emperor penguin is taller than another or has a lovelier voice than another. Something that will make them more attractive to the ladies, or perhaps the ladies more attractive to the men, or maybe just survive better able to avoid those killer whales. And remember that we need to look at the population level. When we're talking about evolution, it could eventually end up in a species that might spread across the world and might become fairly common. The actual changing event could occur within a population or will occur within a population. And recall that a population is a group of the same species living within an area. And it's important that it's an area because remember that an area is an environment which determines the natural selective pressures that they will experience. So we're going to look particularly at natural selection on a population. Yesterday, we talked about allele frequencies and the fact that variation within a population can be measured. Remember that we can measure variation within a population at the allele level. Each individual brings 2 alleles because of their homologous chromosomes, and they can contribute either allele to the future generations. We can calculate homozygous dominant, we can calculate heterozygous, we can calculate homozygous recessive, and then we can calculate for individual dominant or recessive alleles how frequent those are. So today we're going to look at how natural selection actually acts on those things, and there's going to be some trends that we need to explore. Again, our goal is to realize that populations, not individuals, are evolving. And maybe I haven't said that before, I can't quite remember. An individual cannot change its genes, at least not purposefully. Mutations can change an individual's genes, but an individual itself cannot change its genes, and natural selection can't change our genes either. Natural selection can say, this one's better because of its genes, this one's worse because of its genes, and it doesn't change those genes, it just changes whether it's alive or not, or it changes whether it breeds or not. The genes themselves, the DNA does not change, it's just the success of that organism. So it's a population that over time evolves or changes, the gene ratios, the amounts of each gene that we see. Natural selection has to act on the distribution of the traits, the distribution of the phenotypes. It can't act on the genotypes. It can't tell that a brown-eyed person might also have the allele for blue eyes. Remember that your phenotype is what is expressed, and your genotype is kind of what's under the hood. In this case, natural selection has to act on what is showing. And when we talk about a distribution, we're talking about this range of traits. If you're talking about distributing candy to the class, it's how you pass it out. Our phenotypes generally exist in a range. So there's like short to tall, and there's medium within between. There's white to black, and there's medium in the middle. But generally, there is kind of a pattern in that distribution. When we look at human height, we can go from short to tall, as I said, we can do medium, and medium does tend to be most common. And that's going to be related to genes. We're looking at their phenotype, but it is related to their genes. So make sure you have, actually from the previous slide, hopefully you got that, populations, not individuals, evolve. And that was the first thing in your notes. Sorry, I didn't point that out. And now you have natural selection acts on the distributions of traits. Populations or phenotypes in a population range in type, but generally exhibit a pattern in trait distribution. Sorry, I didn't point out you need the previous slide and you need these headers. A little bit different than normal. You can pause there if you need to catch up. So remember that natural selection acts on that phenotypic distribution, and it can actually do that in a variety of different ways depending on what is being favored at that time. Here's a picture that I like to use to illustrate the range of traits that we could start with. If we look at human populations, these are actual people arranged by height. So on the far left over here, we have I believe these are cadets. They're conscripts, 60 years ago. We have a very short cadet, and there's not very many of those. We have a tall cadet on the right. There's not very many of those. And as you can see, there tends to be kind of this average in the middle. We're going to describe this based on graphs. If we were to draw a line over this, you might notice it kind of looks like a hill if we drew a line across all of the heads of that last person in the row. So what we could call this is the normal distribution. A normal distribution is a population where the mean value is the most frequent. And another word for mean is average. So if we're looking at human heights, average height tends to be more common rather than short or tall. So in a normal distribution, a population where the average value of a trait is most frequent. With our rabbits down here, as you can see, it's got that nice slope like a hill, or as we will call a bell curve. In these rabbits, they can be dark black, they can be black and white, or they can be white. And in this particular one here, white tends to be the medium value, the in-between, and it is more common. So the higher the hill, the more individuals that are in that population. Now, a normal distribution is a population that is either before evolution or one that is not experiencing evolution. So let's put these up here so we can think about it. So the frequency of a trait decreases as it approaches each extreme. So the more in the rabbit population, you have less of the black rabbits because they are more extreme. If you have the black and white rabbits, you again have less of them because you have more of the extreme. You have more of the white rabbits. So if I go toward the edges, the height of the hill or the graph, the curve, drops down, representing there are less individuals. The higher the curve, the more individuals. So this is what we call a bell curve. And as I mentioned, traits that are not going through natural selection have a normal distribution. So these are populations that are either before evolution or before natural selection, or populations that are not experiencing it. So this is kind of like what you start with. Now, most populations don't start here, honestly. Most populations have kind of gotten to here over time, and now they're experiencing a new shift in their environment, which is going to change them differently. But a normal distribution, as we kind of can call it, is what you start with before evolution, or if you're not going through evolution. Remember, you need to write your answer to these on your homework sheet. So this is question number 1. You don't have to write out the entire question, but I would like you to write the letter and the answer of your choice. So please, on your homework sheet, which is page 321, before you go and write any of the answers, go ahead and write these on there. So natural selection that changes the distribution of a trait to favor one extreme phenotype is called. See what you think that you would call this. We haven't actually talked about it yet, so this is a preview question. What do you think we would call it if we're favoring one trait over the other, one of the extremes? So in our rabbit question, what would we call it if we're favoring the black over the black and the white, or over the white? Again, this is a preview question, so I want you to challenge yourself. Do you think it would be disruptive? Think about what happens if you disrupt something. Like if I saw a fight and I decided to disrupt the people. Do you think if I'm favoring one over the other, is that disrupting? Stabilizing. If I think stabilizing, I'm thinking like trying to bring back to a medium. So if I'm favoring one trait, one extreme over another, am I bringing that back to a medium? Normalizing selection. We just talked about normal distribution. So that's where you have more generally the average, the middle phenotype. Or do you think it's going to be directional selection? So if I think directional, I'm like this one or that one. I'm going right or I'm going left. So again, make sure that you write your answer on your paper. Put number 1, and if you want A, put A, disruptive selection. We are going to talk about this. This is just a preview. But a lot of times I like to point out how the words kind of describe what they do. So I'm making you think about it. Think about what disruptive would mean. Would it be, favoring one over the other? Think about stabilizing. Would it be favoring a middle potentially? Think about normalizing, which is kind of a harder one. And then think about directional, one or the other. So again, take a stab at it. So let's actually talk about those. If the traits, as I've said, are not going under natural selection, they will have a normal distribution. So these populations, all phenotypes, have an equal chance of survival. However, as we know, sometimes the environments do change and a certain phenotype becomes an advantage. So if we favored brown eyes would be the more common trait over time. We'd see less mating with humans who have blue eyes or less mating with humans who have green eyes. And over time, brown would become more common. Or in the rabbit population, if all of a sudden the black rabbits started dying off for some reason, maybe the environment became very snowy and it's just really easy to see them. We're going to favor the white rabbits in that case. So what works at one time doesn't always work for the rest of the time. Natural selection is going to favor certain phenotypes, and that will actually cause them, as we said, to become more common in the population. This should be the last thing on your first page of the notes, by the way. So without natural selection, we're going to have a normal distribution. But in most cases, there is natural selection. In most cases, there is something saying this is better or this is not. So let's talk about what happens. First off, we do need to mention microevolution. When we're talking about evolution, it starts with microevolution. It starts with this change in the allele frequencies. Remember that allele frequencies are at the genotypic level. So we're having natural selection act on the phenotype, and that is affecting the genotypes. If we're acting against the homozygous recessive, we are removing the homozygous recessive ones from the gene pool. We're removing the recessive alleles from the gene pool. And if we take enough of them out, we might lose that recessive allele overall. So microevolution and a change in the allele frequencies over time happens within a single population. It's happening within one group of beetles in this case. The first generation, we had an allele frequency of 75% for the green and 25% for the yellow. But in the second generation, we see that that's starting to drift just a little bit. For some reason, the yellow is becoming more common. This could be caused by natural selection, but it's not always. We'll talk about when it's not always in a future presentation. We're going to focus on the natural selection one as well. So some event is occurring to this population of the beetles, and we haven't seen a huge shift in phenotypes yet. We haven't seen a new species being created, but we have seen those allele frequencies start to tip more toward the yellow than they had previously. So make sure you have the definition for macroevolution. Make sure you have those two bullets below it filled in. And again, go ahead and pause there if you need to. So when we talk about patterns, there are patterns we can see in how natural selection changes allele distribution, how it changes that bell curve. There are 3 ways that it can do it. And you might remember these from that previous clicker question, which we never use clickers, but same idea. There can be directional. Again, I like to think directional like left or right. There can be stabilizing. I like to think like I'm stabilizing a table toward that middle. I want it to be flat. I want it to be even. And there can be disruptive. In that case, I like to think I'm breaking up a fight and I'm dividing the 2 people. I'm separating them. So keep in mind what these terms are actually telling you, because they're going to help you remember these 3 things. Hopefully you've written that down. So we're going to start with number 1, directional selection. Directional selection would have been the answer that you wanted for our previous clicker question. Oop, too far. Directional selection is when one is favored, one extreme is favored. So we're causing the allele frequencies and the phenotypic frequencies to shift from average to one of the extremes, one or the other. In this case, with the rabbits, we could be favoring the black. There weren't very many black rabbits to start with, but now black is great. Black is keeping them alive. Black is making them breed. The white, which was the average, is for some reason not very good anymore, and the black and white is also not very good. But black is where it's at. So it was once rare, but now it's starting to become the norm. So if we look at this graph, the dotted line was that original normal distribution that we said was before natural selection or without natural selection. The one on the top shows you for bacteria resistance to drugs. Before you apply that drug, the bacteria had kind of an average low drug resistance at this middle below the dotted line here. But if you've heard of drugs ever building resistance in the bacteria are gaining drug resistance over time. Those that are more resistant to the drug are living on, and they're becoming more common. So the moderate phenotype is now shifting. Those that are less resistant are dying off. Those that are more resistant are becoming more common, and those that are highly, highly resistant are becoming a thing. In this rabbit population here, again, we're favoring one extreme over another. So let's say this was a snowy environment where we could get away with being white. We could get away with being black because there were enough shadows. We could get away with being black and white. But all of a sudden, maybe there's no longer snow and there's just a bunch of dark soil. Now the predators can easily find the white ones or the white and black ones. They're killing those off, and the number of dark rabbits is becoming much more common. So if we're thinking directional, I usually think going in a one direction. Again, I can go left or I can go right. I like to make that motion with it. So moving to one side or the other. We had the middle, now we're moving to one side or the other. Another thing that can happen is stabilizing. We're favoring the intermediate, we're favoring the average. As I said, I like to think of this more as like, stabilizing a table. So we're going toward that middle. This is when the phenotype frequencies stabilize around the average. They're not shifting to one side or the other. They're shifting toward the middle. So we are still going to have a change, but in this case, we're going to see our hill get taller. In this case, with our rabbits, the black is bad, the black and white is bad, and the white is wonderful. So we are going to favor a phenotypic frequency in the middle or around the average. The extremes are going to be getting them killed at this case. You already have the picture there in your notes of the rabbits. We're selecting against the extremes. Again, pause as you need to. The rabbits that we've already talked about are down here. Again, the dotted line is the original normal distribution before anything happens. After is this final one. In this case, black rabbits and black and white rabbits are dying off in great numbers. So we're decreasing their numbers. Notice how the curve is dropping. And because those are dying, the white rabbits, compared to the rest, are becoming more common. So we are stabilizing toward the center. So directional, I like to do a side, like shoving off to the side to help me remember. Stabilizing, I like to do it kind of pulling my hands inward toward the middle to help me think, okay, I'm stabilizing it. I'm building it up, if you like hand motions. If we look up here, there is a type of woodpecker and a type of wasp that eat these things called galls and gall flies. So if we look at a gall on a plant, it is kind of a swelling on the plant that you might have seen. Let me see if I can pull it up. Here we go. Yes, you can see that. Awesome. So you might have seen these on plants a couple times. These are actually caused by either viruses or bacteria, or in this case, the one they're specifically talking about is a wasp. So the wasp will go to that plant, and it might not be this gall specifically, but one of these, and it will lay an egg in it. And that will cause the plant to actually kind of mutate and form this growth around the egg so that the egg is protected and that it can grow. So what's happening, the wasps had, to start with, this dotted red line, a variation that caused them to create some small galls, some small swellings, and some large galls. And that was kind of normal. But then these woodpeckers learned, ooh, these are tasty, and we loved these. Oh, crap. Sorry. The gull flies are doing that. Sorry. The gull flies are creating the gulls. The woodpeckers learned they're going to eat the large gulls, and the wasps, which are not making the gulls, sorry, that's the gull fly. The wasps learned that they could eat the small gulls. So these gull flies, which are making these large or small swellings on the plants, are now being favored to make medium-sized gulls. If they make too small, the wasp is going to eat them or going to break into it and kill their offspring. If they make too large, they're attracting the woodpecker, which is going to do the same thing. So we're favoring the middle here. We're not favoring the small, we're not favoring the large, we're favoring the middle. If it was directional selection, we'd be favoring either the small or the large. But here we're stabilizing in the center. And then the last one, directional selection. We're favoring both of the extremes and we are disliking the middle. So the extreme phenotypes are going to become more common over time. We're selecting against the average. In humans, this would mean we're selecting against the medium and we're choosing the short or the tall. This is what can lead to actually the formation of new species. The previous ones can lead to a change in species over time, which if it lasts long enough could be recognized as a new species. In this case, it's actually splitting, so you might end up with two new different species. So we're leading to potentially this selection of a new species or two different species in this case. I'll give you some time to finish writing that one. As you can see on the graph of the rabbits, instead of going to one side as we would with our selection that's disruptive, or going to the center as we would with stabilizing, this one we're going to both sides. So we're favoring both extremes. One is becoming more common over time, the other's becoming more common over time, and the average is kind of dying off. So here are our rabbits again. They started off with that normal distribution of black being uncommon, white and black being uncommon, and white being more common. But now, for some reason, white is horrible, and black and white are okay and actually favored. So we're killing off all the white rabbits, and black ones are starting to breed with black rabbits, and white and black rabbits are starting to breed with black and white rabbits. And those are becoming more common. We're separating these two populations, potentially. If they eventually become different enough, they might become two different species. This has happened with some birds. So there's a type of bird, buntings, that originally started out as kind of a black and brown bird. But for some reason, blue birds started to like blue birds better. Brown birds started to like brown birds better. And they didn't like the ones that were in between. The ones that were both black and blue had less luck with the ladies. So over time, the brown ones became more common and the blue ones became more common. But the brown and blue kind of died off. So we're going to be separating, we're going to be disrupting that population. So we started off with the normal, and now we're moving to both extremes. So again, I kind of like hand gestures. Disruptive moves to one side or the other, both sides. Our directional moves just to one side, and our stabilizing moves toward the center. And please feel free to ask me about this tomorrow. So again, disruptive, moving to both extremes. Stabilizing, moving toward the center, and here the blue one's the after, and directional moving in one direction or the other. I don't particularly like that directional shows you without the normal curve. They are showing you favoring one extreme and then moving to the other extreme, but that can happen as well. Now, I do believe that's the last thing in your notes, but please make sure you're staying attentive. Please make sure you are still paying attention because you have to answer on your homework sheet these questions that are coming up. So number 2, which you should write under number 1, again, make sure you put the letter and the word that goes with your answer. You should be able to answer all of these now from your notes. In a population of birds, intermediate beak size is selected against. So when we say intermediate, we're saying average. So we're selecting against the average. And both small and large beaks are favored. So we like the small and we like the large, but we hate the middle. What type of selection is this an example of? Is it directional? Think about, what does directional mean? I like to think, shoving to one side. Is it disruptive, where you're separating? Is it normal, which is not really a type of selection, actually. It's just kind of before selection. Or is it stabilizing, which likes the middle? So in this case, we're selecting against the middle, and we're favoring both of the extremes. So please write the letter and the word of your answer. Pause if you need time there. Number 3, what do we call an observable change in allele frequencies in a population over time? Now, we've said this as the big word before. We said, a population is changing over time, and we said it's this. But today we mentioned specifically when you look at allele frequencies as opposed to the entire species or whatever changing over time, that we will call it one of these. Is it selection? Is it microevolution? Is it distribution? Or is it recombination? So please write your answer on your sheet. Again, pause if you need more time. 4, writing on your sheet again, a population that is not undergoing natural selection. So this is either not experiencing natural selection or before natural selection. What do we call that curve? It's a bell curve, if you remember. But what do we call that type of distribution that creates that bell curve? A, normal, B, disruptive, C, directional, or D, stabilizing. And then last but not least, if we have stabilizing population or stabilizing selection, what is happening? In stabilizing, I like to use the hand motion where I'm bringing them together, if that helps you think. Is it A, the population shifts toward one of the two extremes? Is it B, both extreme phenotypes shift toward the middle, so we're favoring the average? Is it C, the intermediate phenotypes becomes more common, so that means we're not disliking the extremes, we're just liking the middle one better. So that's a little bit different than than B. B, we don't like the extremes and we're shifting toward the center. C, we don't mind the extremes, we're just getting more in the center. Or D, the intermediate phenotype is becoming rare, meaning it's dying off. So B and C are a bit of a challenge there. Okay, that is the end of your notes. Please make sure that you have all of them filled out because you will have a notes quiz eventually, as you know. If you have any questions, please be sure to ask me tomorrow. I should be back unless something horrible happens, and fingers crossed that it won't. So let me remind you again, do not forget that you have homework due tomorrow. It is page 321, 1 through 5. You can find that, I believe, on Google Classroom and also in your book if you just want to go the old school way. Make sure you have these clicker questions in there with your answers. And if you did get something wrong, if you did figure out that something was wrong, don't worry about going back and fixing it. That's okay. I'm not grading you for correct on that one. Okay, thank you. Don't forget to do your homework. Bye.